Welcome to the second video of the fourth class time series of videos for instruction. We left last time with a look at the molecular orbital diagram for carbon monoxide. In this video we will discuss how molecules, electrons in those molecules can interact with light. And then we'll look at forming crude molecular orbital diagrams for multiatomic compounds. So an interesting feature of these molecules are the electrons exist in these molecular orbitals, and you can see there are energy gaps between the molecular orbital system. In fact, there's a gap of energy between the sigma prime molecular orbital and then the next highest in energy molecular orbital, pi star x or a pi star y antibonding molecular orbital. And what's interesting is when light hits the carbon monoxide molecule, if a photon happens to be of the perfect energy gap in terms of its wavelength or frequency, whichever way you want to look at it, it can be absorbed by one of the electrons, and then the electron will make a transition between this sigma prime bonding molecular orbital and the pi x pi y star antibonding molecular orbitals. And so what I'm saying is the electron configuration in the ground state can be written or symbolized like this without drawing your diagram. Maybe a photon comes along and promotes one of the two electrons in the sigma prime molecular orbital up to the pi x star pi y star set of degenerate molecular orbitals, and that would be carbon monoxide in the first excited state. We symbolize energy corresponding to a photon of light as h nu. We know the energy equals h nu, Planck's constant, times the frequency. And of course, the speed of light is related to the frequency by wavelength. So what does that look like on the molecular orbital diagram? That looks like, it looks like this. This is carbon monoxide in the first excited state, where we've promoted one electron from the sigma prime molecular orbital up to the sigma, or the pi x pi y star antibonding molecular orbitals. And just to revisit the idea of bond order, we could think about the bond order for carbon monoxide in the ground state. That is 8, the number of electrons in bonding molecular orbitals, minus 2, the number in antibonding molecular orbitals, all divided by 2. That's a bond order of 3. And we had that sense that there would be a triple bond for carbon monoxide from the most favorable Lewis dot structure for it. In terms of the first excited state, the bond order for carbon monoxide now becomes 7 minus 3 because we promoted an electron from a bonding molecular orbital up to an antibonding molecular orbital, all divided by 2, so that would be 2. So carbon monoxide in the first excited state is going to have a weaker bond than in the ground state. Interestingly, the wavelength of light that does this is about 154.6 nanometers. You could calculate the energy that would correspond to that gap, and you would come up with a figure of about 8 electron volts. This is a whole subject in astronomy where astronomers can look at light that passes through a given object, say the tail of a comet, and they can tell what kind of molecules are in that in terms of the light that is being absorbed and potentially the light that is being emitted when those excited molecules fall back, have their electrons fall back down to the ground state molecular orbital configuration. In fact, interestingly, sunscreen. Many sunscreens work on this principle. You slather some organic molecules on your skin, and they have molecular orbitals that are tuned such that the electrons in them can absorb UV light to be promoted up to antibonding molecular orbitals. And then instead of releasing light as they transition to the ground state again, they actually radiate energy in terms of vibrations. Anyways, let's consider ethane for a crude molecular orbital diagram, and we'll get into some more complex molecular orbital diagrams in the next video. To construct a crude molecular orbital for this more complicated multi-atomic molecule, there are a few rules. First, identify the number and type of bonds in the molecule. Well, we have 6 carbon-hydrogen bonds and 1 carbon-carbon bond. It's kind of nice to have a relative sense of energies. I don't know if you remember from general chemistry, but the dissociation energy for a typical carbon-carbon single bond is about 88 kcals per mole on average. It varies for various types of carbon-carbon single bonds in terms of what's around them. But we'll take 88 kcals per mole as a good general estimate for this type of molecule. The dissociation energy of a carbon-hydrogen bond is 104 kcals per mole. Wow, what does that really mean? Well, that means a carbon-hydrogen bond is stronger than a carbon-carbon single bond. It's kind of nice to know that, especially since the weakest chain in a link is typically the one that breaks first. Anyways, knowing this, we can go ahead and set up our crude molecular orbital diagram. In terms of energy, we would expect to have 6 sigma CH bonding molecular orbitals, 6 sigma star antibonding carbon-hydrogen molecular orbitals. A little higher in energy than the sigma CH molecular orbital, we would expect to find the sigma CC molecular orbital. Why is that? Well, we just discussed that the dissociation energy for the carbon-carbon bond is less than the dissociation energy for the carbon-hydrogen bond. The carbon-hydrogen bond is in a deeper well, so it takes more energy to bring it out and break it, whereas the carbon-carbon bond isn't in as deep of a well, only 88 kcals per mole, so it's a little higher than all of these. Another way you could think about that is what really are the orbitals that make up the carbon-carbon single bond, and that would be an sp3 hybrid overlapping with another sp3 hybrid. That's going to be a higher energy combination than an sp3 hybrid overlapping with a 1s atomic orbital. If you didn't get that, maybe you can ask me a little bit more about it at an actual class or actual class session for this particular class time. So I think that pretty much covers our introduction to forming crude molecular orbital diagrams for multi-atomic compounds. We'll try a little more complicated one in the next video. I will show you the very difficult way to think about it at first, and then I'll show you the easier way, and you'll probably be wondering why I tried to complicate things and show you the difficult way of thinking about things first, but really it's all the same thing in the end. Anyways, until the next video.